In this video, we're leaving the Rhino interface to enter the world of Google Colab. Google Colab offers a remote computing interface using Jupyter notebooks to create shareable and open source code within the browser environment. This video is going to be structured in 3 parts. The first part is going to be an introduction to Google Colab, Jupyter notebooks, and their interfaces. The second will be an introduction to OpenCV for image processing with Python. The third is going to be an introduction to AI-assisted programming using Google's Gemini inside of Jupyter notebooks, as well as ChatGPT brought into Google's Jupyter notebooks. We'll take a look at how each of the AI assistant algorithms help us to program and what the errors or downsides of each might be. To supplement this video, I've constructed 3 Jupyter notebooks already stocked with information and helpful tips in order to guide us through. In this video, I'll be going through each of these notebooks, describing what each of the segments mean, and adding additional descriptions. We'll perform a couple of tests by writing our own code and running it within the notebook. Finally, we'll end with looking at an application for this type of image processing inside of Rhino via texture mapping. So let's go ahead and open up our notebooks to get started. With your browser open, we should see a similar page to this. This is the introductory Google Colab notebook. This notebook refers to other notebooks developed both by Google and Adam Lamy. Both of those notebooks and this one explore a couple of the operations that we can perform, as well as the interface of Google Colab's Jupyter notebooks. In this introductory Google Colab notebook, we will explore some of the basic interface options. Each method is separated into its own coding snippet and can be run separately by clicking the play button to the left. If I hover my mouse over any of these cells, you'll see that some of them which are actually just text-based cells, also known as markdowns, which we'll get to at the end of this page. Some of them don't have play buttons next to them, meaning that they are text and not actual code. So text cells don't run because they're not code, but coding cells do run. So if we hover over this one that has our green comment, we can see there's a play button next to it. So we'll get into running these and options for that, as well as outputs from it in a moment, but it is important to know that there are these 2 types of cells on the page. So at the top of this notebook, we have a bit of a description just describing what we're going to see in the notebook, as well as some general introductory interface options. Like most software, we have menu tabs at the top. We have File, where you can save, open, or move documents. Since this is built by Google, we can interface with our Google Drive to store the files, both the actual notebooks as well as files we're interfacing with, inside of Google Drive. And we'll actually take a look at a component that's made specifically for making that connection between this notebook and our Google Drive. Then we have Edit to perform certain edit actions, like undoing the cell or cut and copying. Then we have View, where we can hide or adjust the view of a particular cell. Insert to insert a code cell or a text cell. So I mentioned that there are 2 different types. So this is one of the ways that we can do that. We'll take a look at another way, which is more often used, which is directly accessible inside the notebook itself. And then we have an option for runtime. Since this is a remote computing interface, this means that all of the code is not run on our local machines. So it's not run on your actual machine that you're looking at right now to watch this video. Instead, it's run via the browser connecting to a remote server. This means a couple things. It means we have access to incredibly powerful machines that Google gives us access to so that we can run more computationally intensive programs. Also, it doesn't wear on your computer's resources, meaning you could run a render or something that's taxing on your local resources and it wouldn't be affected by Google Colab running in the browser. So this is really helpful when we start working on these kind of dual processes in parallel. In our runtime, we have options to control the connection or to perform certain actions related to the connection. So what do we see here? We see run all, run before, run the focus cell, run selection, and run after. What do these mean? They're just options for running particular cells on the page, so particular bits of code on the page. So each of our coding cells can be separated as individual cells and run separately. Meaning, if we wanted to run all of them on the page, we would select Run All. If we wanted to run the ones before wherever we've selected, we would run Before. And if we wanted to select all cells after, we would run After. And if we had one selected, we would run Selection. Now the additional options, some are grayed out here because we haven't actually connected, and I'll show you how to do that in a moment. But there are additional options for disconnecting and deleting, and then restarting the session or interrupting the execution. What this means is that once we establish a connection, if we want to, for whatever reason, restart our connection, maybe we're encountering some error and it's a persistent error that we can't figure out how to fix, and we know our code worked the prior day, but for some reason it's just not working. One highly recommended suggestion is that you just go ahead, take a pause, disconnect and delete your runtime. What this means is that you'll disconnect from that particular server. So you'll disconnect from Google server, the page will refresh, you will lose the current files that you had uploaded to that prior server because Google will delete those from that server, but then when you reestablish a new connection, you'll have a clean connection with a new server, and then you can re-upload whatever files. So it's important that before you disconnect and delete, you do save your files. That's not just saving your notebook, that's one thing which you can do as well, but it's most important that the files you've uploaded to the server, if you're working with any files, which again, I'll explain more in this video, all are saved before you disconnect and delete. Two other important options here. One is change runtime type. So if I click change runtime type, we get some information about what type of runtime or what type of machine we can actually run on. So we can use a hardware accelerator, meaning a GPU accelerator. So we could select these if we knew that we needed some acceleration. Let's say we're running a machine learning algorithm and we want it to run faster. We can choose an option to run with this acceleration type. We can also choose to run in R or Python. By default, we're going to stay in Python as that's familiar to us. Then we can also select to run with a high RAM instance, meaning that we would be able to compute a larger amount of data per run. I'm going to hit cancel because for now we don't actually need to worry about that. And then the last thing is manage sessions, which would just tell us if we had any open sessions. So you can see actually I have one of the files we're going to be going through currently active. So 1 minute ago it was active. So if I wanted to disconnect, I could disconnect here, terminating other sessions to allow us to connect to this particular Colab notebook. So I'm going to go ahead and do that, terminating those other sessions and hitting close. So now we have no sessions open, meaning we can open and connect to this notebook. Now how do we connect to this notebook? Well, we go to the upper right. Mine says reconnect, but if you're connecting for the first time, yours will just say connect. If you click on this connect option, you're going to get 3 orange dots and it will say connecting. This is the process of connecting this notebook interface to the actual server. Once it's established the connection, you'll get a green check mark, and then you'll also get some information about the RAM and disk usage. The RAM is going to be the memory use on that particular server, whereas the disk is the storage space used on that particular server. So you can see, since I have Colab Pro, I believe it's giving me a little bit more storage space, possibly also more RAM space here, but I have 225 gigabytes of disk space at my disposal, and 35.39 is taken up by default. So those are not my files, those are just the files on the server already, but I have that additional 200 gigabytes to work with. So with that check mark showing up, we can now jump into the notebook. As I mentioned, the top cells here are just text cells. If we hover over the middle in between two cells, so the kind of middle line between two cells, it gives us an option to add a code cell or add a text cell. If I click add a code cell, it places this kind of dark gray box and I can now type in here. But if I just type text, this is text, you can already see that it's actually color coding this for us. Why is it color coding this? Because Python, or our code cell, our notebook is reading this as Python code. So it's already trying to prepare it to run in Python. That's because that's a code cell, and a code cell has an option to play or run. We'll come back to this, but also now it says start coding or generate with AI. So actually Google has built Gemini into these coding cells, allowing us both error correction, debugging, and troubleshooting, which is incredibly useful. But the other thing is we can actually directly generate code just from text prompts. So if we have an idea of what we want to structure, we could just start with generating code using Gemini. Alternatively, we can also use ChatGPT by OpenAI. I'll get into a little bit about both of these models at the end, and we'll take a look at a couple of examples of the code that they generate. I will warn you though, the interface with both of them is not very useful if you don't already know the structure of programming. If you're not able to guide them, then how do you expect to generate code that is useful to you? If you're not understanding what's being written, how can you make use of it as a designer? So to delete this code cell, we can click delete. If we wanted to move this in our notebook, let's say we want to move this to the top, we click the arrow up, that moves it one cell up. So we've jumped one of these text cells. I can move it up again, and then we could move it down with the down arrow, and to delete, we just click delete. If we wanted to make a text cell, we would hover over that text option, click plus, and now we can type, this is just a text cell. It does not run code. And then if I click away, we can see that there's no play button because we've just created a text cell, so it's just giving information to us, the user of this notebook, to make it a more enjoyable and user-friendly interface, giving us some descriptions that we can learn from. I'm going to click delete on that, and we're going to read through a couple of these descriptions. This notebook is set up in a way that hopefully you're able to go through and understand on your own. But this video is also supplemental to that so that I can give additional descriptions and walk you through how you can learn on your own using these three notebooks. We just have a couple of links at the top. So one is the link to the playlist that you're currently watching. And then there are two other links, which are the reference notebooks that I've referred to in building this notebook for you all. There's also some descriptions of general interface inside of these Jupyter notebooks, such as the fact that there are code blocks and text blocks, and to execute a cell and proceed to the next one, you can either hit play and then play on the next one if you wish to proceed, or you could select it, so left click on that cell and then hit shift and enter simultaneously in order to run that cell and then move to the next cell. You can modify the code as well after running or before running, and then rerun, repeating these same actions. To begin, run each of the following cells by pressing shift and enter simultaneously, or by pressing the play button next to them. And then I have a bit of information here about Google Colab running as a remote computing interface within our browser. Since we're running this with Python outside of Rhino, we don't have access to Rhino script syntax and other Rhino libraries. However, we do have access to an incredible amount of other libraries that exist in the world of Python outside of Rhino. So in many ways, this will open up our environment and allow us to explore much deeper into the programming language of Python. But to start with, we're going to start with some familiar coding segments that we saw in the introduction to Python inside of Rhino. So in the first code cell here, we have a mathematical operation. We have an instruction saying click on this cell and then press shift and enter to run it. We can either hit shift and enter or click play. If we click play, we see it quickly spin, so the wheel spins with a stop sign. We could click quickly on the stop sign to disrupt the execution, interrupt it, and not allow it to finish. That's if we don't want to wait for it to finish. Now these are going to be really quick because they're quick mathematical operations. If we get a check mark next to our play button, that indicates that it's run the code and it has finished. In this case, since we're just performing an operation that's not set equal to anything, by default our code cell prints that inside of our console. So it's going to output in this kind of output window below the code cell. So we see 2 + 2, a mathematical operation, which is run inside of Python, And we don't even need a print statement. We can just directly print 4. That's because we haven't set this equal to anything, which we'll see in a moment. If we go to this next cell now, we have some descriptions saying this is called a comment. It's a message to other humans. We've reviewed this inside of Python for Rhino, which is that comments are just messages to us, the user or author of this code. So Python doesn't read comments. The program will run the next line since it doesn't start with a £sign or a hashtag, meaning it's only going to run this mathematical operation of 5 minus 4. We can click play and we get an output of 1. 5 minus 4 is 1, so we're outputting 1. Now the following lines define variables called a and b. So we have reviewed variables, so I won't go too in depth into this, but we can set variables just like we did in Rhino with a equal to 4 and b equal to 3. We could also type another variable here, add it in, c equals to 7, and we could add that minus c. So another operation inside of our cell. I've edited this coding cell and now we can click play. We now get 0. Why do we get 0? Because 4 plus 3 equals 7 minus 7 equals 0. What if we make c equal to 6 and then hit play? We now get 1. So we can perform and edit these operations as needed and then click play to recompute and get a new output. The cell below has an equation c equals a asterisk a. What does the asterisk stand for? The asterisk stands for multiplication. We've already assigned a in the previous cell, so a equals 4. If we run this code, c equals a asterisk a, and then c with no equality there, meaning we're not declaring it, but we're actually asking for Python to print this as an output. So if we click play, we get 16, which is 4 times 4. What if we say a times c and set this equal to d? Well, since we just ran c equals that equation, so c equals 16, we should get 16 times 64. So we're actually overriding the prior variable there. So we need to be careful when we're running these that we don't override prior variables if we wish to continue operation with those variables. So each of these coding segments has a kind of memory that gets passed through the notebook. This is incredibly useful because we can play or run individual lines of code within this cell at one time, but we can then take whatever variables are stored above and pass them down below. That's something we want to note though if we don't want to override certain variables. So just keep that in mind as you work with these and build your own. In the next cell, we have d, a variable, equal to a string. So d equals, I just coded in Python. We can change this message by typing inside the quotes. If we hit play, we get a printout, I just coded in Python. If I write in, I just coded again in Python, and hit play, we get it printing, I just coded again in Python. As I've mentioned previously, this is a variable of type string, and the former was a variable of type integer. All of our variable types, lists, and data structures are going to be accessible inside of these coding cells. Now, can you figure out here what a double asterisk signifies? If I hit play, we have b double asterisk a. So if I hit play, we have e equals 81. So 81 equals b double asterisk a. Well, b equals 3 and a equals 4. So what does this equal? A double asterisk signifies raising something to the power of the other variable on the right. So b to the power of a. So 3 to the power of 4, which equals 81. The next section here in our notebook is an example of loops. We're familiar with loops by now in Python, but we can run each of these inside of our notebooks as well. We run them the same way that we do inside of Rhino. So we can do a for I in range, which if we click run, we're going to print that out and get 0, 1, 2, 3, and 4. We can also save a list. So we're storing variables, or string variables more specifically, inside of the list, and then we're looping through or iterating through each item in that list, and then we're printing the item. So we get this is a list. all printed separately. For while loops, we can overwrite that variable and then iterate through until that condition is no longer met by adding to that value. So it started at 0 and then it runs from 0 to 4 because then I becomes 5 and 5 is no longer less than 5. We can also run function just like we did inside of Rhino. So we can structure an addition function that takes in a and b and returns a plus b, and we can just directly feed in values here. So 3 plus 4 is 7. We can change this to 3 plus 5, which is 8, 3 plus 15, which is 18. So we can perform these functions. We can even define a function in one cell and call it in another cell. So let me copy this, make a new coding cell, and just put the call to that function here. And let's change this to 7 and 15. And now we get 22. So we're still able to call that function from a different cell, even though it's defined in a prior one. And that's because this notebook has a kind of memory between cells. Now let's get into the actual interface options and some of the user interface of these notebooks. The next section is mounting to Google Drive. What do I mean by this? Well, this one particular code cell, written exactly like this, allows us to import certain functions from Google Colab's library. In particular, the Drive class, which has a method mount that allows us to access our Google Drive. We then mount it at the location specified here, which is actually a file path. I'll get into file paths and file structures in a moment, but it's important to note, since this is developed by Google, we have a great access between Google Drive and our notebooks. So we can share past data or files back and forth between them. And this allows us to overcome the issue of running on a remote server, which deletes our files every time we disconnect or close the browser page. So if we wanted to save our files or access them, we would be able to run this code. Now, what do I mean by this being a file path? If we click on the folder icon to the left, we can access our root directory or our folder, which we will work with by dragging files into, and then we can use them inside of our notebook. We have to do this because we can't directly access the files on our computer since we're not running this on our computer. We're running this on Google servers. So we have to upload it to the server by dragging it into this window on the left. Now, if we drag something into the window on the left, it will give us a warning saying, ensure that your files are saved elsewhere. This runtime's files will be deleted when this runtime is terminated. We can hit OK, but that warning is saying once we disconnect our runtime, it will delete that file. If I want the path to this file, I need to select the 3 dots to its right, and I could download, but we just uploaded, so we don't need to download. I could rename, delete, copy path, or refresh. I'm going to select copy path. Now if I make a new text cell and paste this, we get the path, which is actually a string, to that particular file. So that's the file path to that image. If we want to preview that image we've uploaded, we can double click on it inside of our tab on the left, and it will open up a preview window on the right. So we'll just wait for it to load, and we can preview that image. So now we get a preview of the image that we've uploaded. We can hit X to exit out of that and no longer see our preview. It's important to note that every time we upload an image, inside of this main folder, it's called content / and then the name of our image. So we have / content / the name of our image. That's because it's located in a folder that this notebook refers to as content. So on our server, we have a folder. That's actually this entire folder we're looking at here. And that folder is called content. So what does it mean when this Google Drive mounting function mounts to content / drive? It means it's going to make a new folder here called drive. And what's it going to do? It's going to take the connection to your particular Google Drive, and it's going to give us access to that under that location. So under that file name location, that file path. I'm going to delete this text cell that we made, and now we can click play to mount to our Google Drive. What's going to happen is it's going to prompt us to log into our drive, and then we'll see our access within our folder system on the left. If I click play, we can allow access, connecting to drive. It will run, So we see the wheel spinning as it connects to our drive, and then once it's loaded, we should see a folder pop up called Drive, which we do now. And we see an arrow drop down. We can click on that. And we now have options for My Drive and Shared Drives. You may not see shared drives if you don't have shared drives in Google Drive, but you should see My Drive. Inside of My Drive are all of your drive folders, so you can access any files directly from there by clicking on the 3 dots and then selecting Copy Path. We interface with this file system by copying paths and referring to those file paths. So inside of Python, in order to get a file from our folder system to our particular script, we need to refer to its file path. That gives Python an exact location to refer to grab that file and do something with it. So we've now mounted that. At the beginning of every notebook that you create, I highly recommend giving an option to mount to Drive, even if you don't plan on doing it all the time. It's sometimes nice to give yourself a reminder that you can access your Drive with whatever notebook operation you might be building. Now let's get into a couple of user interface options. You can actually design the structure, like I've done for this notebook, of your own notebooks, meaning you can change the font type, you can change the kind of text organization, you can even change the organization and contents. What do I mean by that? Well, if we click on the 3 dots and then lines icon on the left, we can actually see the contents outlined of this particular notebook. We can click into Functions, Mount to Google Drive, User Interface Options, Loops, and cycle through each of these sections. How do we define a section? Well, if I double click in, it now goes from what was a nice text-based user interface defining a section, and it shows us the background code of how I structured that. How did I structure that? Well, I actually just typed some information, and in this case, I typed user interface options, I selected it, and then I clicked on this toggle heading. That gave a hashtag in front. We could also just place a hashtag ourselves. And then that now declares this not as just text, but as a section heading. What does a section heading do? Well, it adds it in the structure of our table of contents. It also allows us to minimize the code or hide the code within it. So now if I click the drop down arrow, we now get that expanded again and we can cycle through everything. The text cells as well, you can double click into and you can see the structure within these also. If I highlight any of these bits of text, I can use any of these options like italics, which then puts those 2 words within an asterisk on either side, which performs italics. We can then see the italics showing up in our output text cell. If I double click, I can close that and we no longer see that background code, and now we just see the text. These cells are called markdown cells. Markdown cells contain markdown text. That's text that isn't read as Python code. Instead, you can format markdown text to look nice. Double click on this cell to see the markdown text underneath. Running a markdown cell turns into pretty formatted text. So if we take a look at the structure here, we have a way of referring to hyperlinks within open and close brackets, so we can name that hyperlink a particular name. So that's the link to this tutorial series. We can also make italics or bold by placing in single asterisks or double asterisks. We can also define a bullet point using a dash, and we can double click either into the text to open it up and edit, or double click on it again to close it and hide this kind of background code. If we add 2 tabs before our text, then we get this gray box where we can place some instructions possibly, or maybe variable default values, or anything else that you want, but you get this kind of gray box to be able to write things inside of. Maybe you're referring to something or placing a quote in here and you want to cite some particular thing, then you can do it by tabbing in twice. So I've given an example, tabbing in twice and saying the default value for the variable equals 0.4. To finish editing this, we double click on the right side and it closes back up. You can even embed images. You can do this by referring to a particular URL or website link, which can reference a particular image and be read in your notebook. Or if we double click here, we see that it's actually an encoded image in our cell. We've written out the JPEG compression here, so that it can be drawn directly in our notebook. So now we see that image being represented inside of our markdown box. Also, if we don't like visualizing the code and instead we want to write the code and then give ourselves nice interfaces to focus more on the user experience, making it more accessible for us to interface and access these coding notebooks, then we can use user interface options. I've listed a series here based on Google's own introduction notebooks that go through string fields, raw fields, date fields, number fields, Boolean fields, and then we have options for markdowns in forms. What are each of these? Really, these are each just a bit of code that allows us to input into variables. So we have a variable text, which we could then use Python, which we're doing here, by printing each of these values. So we're storing the value here into that variable value. What else are we doing? We're constructing this interface so that we don't actually have to edit it in our code itself. So we're basically just running Python code, but we can change the values here. This is a changed value. And we can even see the strings on either end of this blank box. So as I type it in, our text value changes. Next, we have a drop-down option, and we can select first, second, or third in this case. If we wanted to change that, we just double-click and change this to first choice, second choice, and third option. So we can leave it like that. And then we had an error because our next input read in the values from our second one. So we just needed to edit that. And now we have a text and drop down. So we could write in text goes here, or we could select from the drop down list. So the kind of background code that stores these values as variables happens on the left side, which we can access by double clicking and double click to hide it again. But if we don't want to look at it, as long as our Python code is structured, we can still click play, and then we get these values printed out. So the Python code is still running even though we're only looking at a nice clean user interface. We can do the same thing with raw input fields. So raw input, we can say 0, raw dropdown, false, play. So we now get a Boolean in our dropdown for the bottom one. We can say a value of 1 for that dropdown as well. We can give it a string for the first value and then an integer for the second. So this allows us to actually change arbitrarily whatever our variable type might be. So raw fields allow us to change the variable type, and string fields read in specifically string values. How about the date field? Well, if we take a look at what's happening here, we have a specific date set, year, month, and then date. We can then format it or select it from a calendar. So let's choose that particular date. So 03/23/2018, and that gets fed into our Python script as a variable. If we click play, we can print that date below. Number fields, we can either have a number input that we type to, which gives us an integer that's still going to be read as a float. So here we have a float, a number slider, which we have a range from -1 to 1. We can change this range inside of that parameter by changing our min and max value. Let's make this -2 to 2. We can also change that step value. Let's make that 0.4. Now it's going to step in increments of 0.4 from 2 to -2. And we can just slide that, and as we slide it and then release, we input that as a variable input to our Python script. We also have integer inputs. This just forces the variable to be an integer. So here we have any real whole number. Lastly, we have integer sliders, which just have a step value of 1. If we double click, we can see that these are of type integer. So that's integer type input, type slider, but we have a step value of 1 here. Then we have Boolean fields, which we can use as checkboxes or true and false dropdowns, which we can see how they're structured here via the param type Boolean or param, and then type raw, and then we can input false or true options. So that gives us a drop-down menu if we use type raw and then false and true options. If we just use Boolean, it just gives us a checkbox of true or false. So if we keep that checked, we'll get a value of true printed. And now we have false in the drop-down, so it prints false. So it's running that background code, but we've hidden that from our view so it doesn't look quite so messy. Now, how about our markdown? Well, inside of our markdown, we can nest a title. You can also include markdown and forms. So we have that text being printed out in our interface, and then we say enter a file path. So it gives us instructions within our form to enter a file path, and then adds a variable file path that reads in a string. What could our file path be? Well, we know our file path content exists, so we could do /content/. That's going to read all of the files or contents inside of our content folder. If we want to print that, we can say print file path. Now play, and it's going to print that file path. If we wanted to list all of the items in that directory, we could use our OS library or system library to be able to interface with our actual system. Now, can you try this? Double click on this cell to see the code that formats this text. Make a few edits and then press Shift and Enter to see what changes. If you want to read more, there's some helpful link on basic formatting for these text cells or markdowns. So if we double click, we can make any edits that we want here and then double click to save them and see how that changes. Lastly, saving your work. There's several options for saving your work in Colab. Now, I already mentioned this notebook is going to delete when we disconnect our runtime. So if you're uploading files to the server, it will delete each time you disconnect from the server. If you have files being uploaded or stored inside of Google Drive because you've mounted it, then it won't delete those files when you disconnect this particular notebook. In fact, we could then open up a totally different notebook, connect to a totally different server, and still access those same files. With this, I'm talking specifically about this notebook to save any edit you may have made. One option is to save a copy in your drive. The other is to download the actual notebook as a Jupyter Python file. Within the notebook, we can also save particular images or outputs by right-clicking and then selecting Save an Image, like a graph or a chart or an actual raw image, to your local drive. So if we go to File, we can see that we have options for Save a Copy in Drive, Save a Copy in GitHub, which we could access later, or just save if we've already saved this file in a particular location. We can then come back to this particular URL and access this notebook to be able to run the code again. Once we're done with our notebook, we want to select this dropdown next to our connection and select Disconnect and Delete. This is going to clear and disconnect our connection to this particular server. We can say yes because we don't have any files that we want to save. Now we have an option to reconnect. This makes it clear that we have disconnected. Now we can go to part 2, which is an introduction to OpenCV with Python inside of Jupyter Notebooks in Google Colab. So this notebook is an introductory notebook for sample methods inside of OpenCV. OpenCV is an image processing and computer vision library which we will explore via this notebook and this video. Each method is separated into its own coding snippet and can be run separately, as we just demonstrated in the introduction portion of this video. Any of these methods can also be combined to compound their action like you might inside of Photoshop. Now, we saw that with the kind of memory between cells in the first examples, but here we actually will have image processing actions that within each cell we can also stack, which we're actually going to do in this file to process it one time one way, and then take that output and process that output another time a different way, and continue on to get kind of compound effects, which we'll see what that looks like as we go through this notebook. At any point, if you want additional documentation on these methods, this is not a comprehensive introduction to OpenCV. It's just a couple of sample exercises using some of their basic methods for image processing, but it's more an introduction of how to integrate some of these things inside of the Google Colab Jupyter Notebook interface. So if you do want additional information on OpenCV, the documentation link is available at the top of this notebook. Now we can go ahead and scroll down and jump into our methods section. So to start any notebook, we need to click Connect in the upper right-hand corner. Right now we have Reconnect. I'm going to click Reconnect and wait for our connection to establish. This initiates the connection to our remote server. Now, when interfacing with image processing techniques, we're going to need to upload images. Right now, our server is entirely empty of images. It has other files, but it's empty of images, or at least ones that we want to reference. So anytime that we know we're interfacing with images, we can go ahead and upload our image files to this particular server that we've just established connection to. How do we do this? Well, we drag the file to the menu on the left. If that's not visible for you, you can just click on this folder icon, which will expand that folder tab, and then we can select our file from our local drive, and then drag and drop it into our menu. We see it loading here at the bottom, and then when it's finished, we should see the file name appear in our folder, which we do here, A2_figures-05. If I double click, we can preview this file in our preview on the right. We now see that image previewing, and we're ready to go ahead and get started with OpenCV. The first method we're going to look at is reading an image. When we want to use an image in Python, we first need to read into our file like rs.getObject reads an object from our Rhino document into our Python file. So we need a similar method in OpenCV which can read in an image into our Python script to be able to do something with it in Python. What is this method called? cv.imread. So first we need to import our library like we do with Rhino script syntax. Our library in this case is called cv2, and we're going to nickname it cv for short so that we can write it quicker. And then we're going to call the method. What method? The method imread. Imread reads an image, so it's a shortened version of image read. That reads it in as particular data that Python can interface with. And then what are we going to do next in this first example? We're going to output or save this image. So we're not actually performing an action, we're just reading it in and outputting it. How can we tell this imread function to read a particular image? Well, it takes in an input of a string value. What is that string value? It's the path to our image. How do we get that path? We hover over our image, select the three dots, select copy, and then we can paste this within quotes, so inside of double quotes, into the parentheses of that method. So this inputs this particular file path, which is the input parameter to this method. Now what do we have below? We have the imWrite function. What does this do? It saves a new image. What does this take in? It takes in a file path or file name. So in this case, just writing the file name itself will save it back in the same location. Well, why will it do that when we haven't declared /content/? Because this code already exists inside of that folder, so it's going to just place the output image in the folder it already exists in. So that's an important thing to note. This output image.jpg is actually the same as saying /content/output image.jpg. So those are equivalent values. So we're giving it a name, output image, output_image with a capital O and capital I, so that exact name, .jpg. The extension is important because an image is not an image without the extension, so we need to specify the file type. And then what else do we need to give it? The actual image data. So this is what Python reads as particular image data. So that's img. If we hit play on this code, it's going to read in our image and output an image. It says true because the action performed is true. It did output an image. Now we can refresh the tab on the left and we see our output image appear. If we double click, we can preview the output image, which is just simply our input image. We haven't performed any action, so why would it change? It doesn't. It looks the exact same. But we now know that our functions are working and we've successfully imported the OpenCV library and performed our first method. Now we can scroll down to much more exciting things like resizing an image. Look at this tiny image. How do we resize it? How do we take the pixels and shrink them down into fewer pixels? Well, we can use a particular method called cv.resize. So in this first example, what we're doing is we're reading in an image, which we're still giving the same file path. If you need to overwrite this, you can go ahead and select the three dots and select copy path and paste in this input again. Make sure you're reading a file that exists in your folder to the left. We can then test the image shape, so a particular property of the image, its shape, by printing that image shape. This gives us information about the image that we've uploaded, meaning its width, height, and then also it's going to give us a (3). Why does it give us an additional (3) when an image is just a 2D array, right? Well, an image is a 2D array with 3 color channels RGB. So by default, it has 3 color channels RGB. Now we can do augmentations to this image structure and change the pixel structure, change that shape. But by default, it's going to be width, height, 3, which is the 3 RG and B color channels. And actually something important to note is by default, OpenCV reads BGR images. So it actually flips them and reads blue, green, red. When we're working inside of OpenCV and only interfacing within it, we don't really have to know that it flips them unless we're specifically declaring a color value. So we're first printing our image shape, and then we're declaring a width and height. What are these width and heights? Well, they're new width and heights to be able to input into cv.resize. What does cv.resize take in? An image, so an existing original image. What else? Well, inside of a tuple, it takes in a width and height value. That's the new width and height. So we're going to make an image of 100 by 200 pixels. What is this last thing? It's the method with which this compresses the data. So it's going to use an interpolated area function to compress or resize that image. This is how it actually determines which pixel gets mapped to which larger, pixel as we resize this image down. So where basically the pixelation happens. And then finally we have an imWrite to save this out. We can also just write this code from scratch again by saying import cv2 as cv image, so store a variable image, set this equal to cv.imread, and then what do we need here? Well, we need the actual file path, and we need to declare it as a string by placing it inside of double quotes. What else do we need? We need a width and a height, so we can say width equals, we could make this even larger. Let's try 300, and height equals 50. So let's totally distort the dimensions of this image. This is going to now force the resize to happen at a dimension of 300, 50. So if we now plug in 300, 50 inside of parentheses, and then cv dot enter underscore area, close parentheses, we now have that function. Now what do we need to do? We need to write this image to our server. We can call this resized image again .jpeg to differentiate between the code above and this code that we just write below. Close out that string, hit comma, feed in that image to our image, telling it which image to write. Now we can click play on the first one. It says our original image was 3,328 pixels high and 6,798 pixels. If we click refresh, we actually get an output resized image. What is that output resized image? That output resized image is now 200 by 100. What if we click play on the second one? And now hit refresh, double click to preview that one. We now get a distorted image that is 300 pixels wide and 50 pixels tall. So that's how we update code and work with this particular function, but this is going to be very similar for all methods inside of OpenCV. Now, what if we wanted to make sure that the aspect ratio is preserved when we're doing this resize action? Well, we can figure out that ratio by doing the math ourselves. How do we do this? Well, we already used a image.shape printout to identify the shape of an image, the shape property, and the first index value we actually see is the height. So we actually have these backwards here. So the first one is the height, and the second one is the width. And then we can now flip these and give width, height. So now we're going to get a printout of the shape. We're going to read those in as values h and w. We're then going to set a resolution value r. So r equals 300. What does our new width equal? Our width will equal that 300 pixel value. What does our height equal? Well, our height is a ratio of height times r over w. And we have to set that equal to an integer because we're feeding it in as a pixel value. You can't have half a pixel, you can't have 0.2 of a pixel. You need an integer value for pixel values. So that gives us the dimensions of our new image. Now we can click play and refresh, and we see our image printout. What if we wanted a larger image, say 1800 pixels in width? We can click play, select refresh, and now we can preview that much larger image. Now we're starting to get back to our original resolution. So that's just some clever math to be able to interface with the resize option to preserve the aspect ratio of our image. What about rotating an image? Well, to rotate an image, all we need is the method cv.rotate, feed in an image, use a rotate transform, cv.rotate_180. So this auto performs the rotation of an image, which here we're going to rotate 180 degrees. We're now stacking the resize and rotate, so when we click play, we're going to output a rotated resize fixed aspect ratio image, and if we refresh, we see that show up, and we can preview this image. We could also just remember the memory of our previous code, and we could delete everything before the rotate and just read in that last image value, meaning the image value here that we have in the last code segment would automatically just be input or applied to this next one. So this is a way that we could kind of go back and forth between two code cells by making an image, setting it as a variable, performing an action, going to the code cell below, referring to that same variable but not overwriting it, click and play, playing that, now updating that variable at the very end of the action, going back up to the top, and you could kind of create your own recursion without even structuring a function, although these also work with functions, meaning they also work with loops and functions and classes and anything else that we have written inside of Python. So we can interface in complex ways, but we can also do it simply like we're doing it right now. So that's going to turn our image around 180 degrees. What else can we do? We can desaturate the image. Now this is a black and white image, I am aware, so it's not very exciting to desaturate. However, the method for desaturation is to convert the image to gray. So we use the particular method, convert color. What do we feed in? We feed in image, and we feed in the transform color_BGR to gray. Why does it say BGR? As I mentioned, OpenCV reads in blue, green, red channels, not red, green, blue. So it's converting it from blue, green, red to grayscale. So we get a grayscale image. Now if we click play, we'll have that show up in our folder, but as I mentioned, this is going to look the same. Why? Because it was already grayscale. One thing to note here though is if we print our image, so we can just say image or actually type out print, either one works. If I click play on this, so we can print our image, click play. Now, this is interesting. What do we see in the printout? We see one list, but it's a flat list. Well, it's a two-dimensional array still, so it is a 2D image, but it's not a three-dimensional array like our prior ones, right? It's not a width, height, and 3 color channels. It's just a width and a height. Why is that? Because with grayscale values, you only have one color channel, 0 to 255 in gray. So it's not actually going to take in RGB values. It's not taking in 3 channels. It's actually converted the structure of that image to just one channel, one color channel, 0 to 255, all ranges of gray. So from white to black, gray. What's next? Thresholding an image. Thresholding an image takes the brightness values of an image and creates a black-white binary image output. Binary image output is really important and key there. So this particular one that we're using is a little bit of a more advanced one. We're now stacking our resize, our rotate, our convert color, and then what are we doing? Now we're calling adaptive threshold, which takes in an image. What else does it take in? It takes in a threshold value, so the value at which the threshold will be taken, and then an adaptive threshold Gaussian C transform. So that's a particular transform within the CV library, as well as threshold binary. So this is, again, a particular transform. And then we have a kernel input and a constant value here, which if you're interested, again, take a look at the documentation. It explains what all of these are in depth inside of the documentation. Just go ahead and search OpenCV and then this name of the method, and it will give you plenty of information to read through. Now if we click play, what's this going to output? this is going to output that binary image, which gives us that black and white value of our math surface. What's next? Next is cropping an image. Now this actually isn't an OpenCV function. Well then, what is it? This is actually just list slicing. Now, I mentioned we have a two-dimensional array, and this might be a little bit too complex for everyone to understand, but it's essentially just a nested looped list, right? So when we were building those math functions and we used U and Vs, think of an image like a set of U and Vs, right? We have columns and rows. So that creates a 2D array. So how can we operate with a 2D array? Well, we can feed in two index values. What if we want not just, a particular pixel at those two index values, but we want more than that. We want a range. Well, we can use list slices. So these slices allow us to say from the 40th pixel to the 200th and the 100th to the 400th. Now if we click play, we can, not threshold, but our cropped image. So now we get an output of our cropped image. What if we want an even tighter crop on the middle here? Okay, well we can do that. 140 and 200. So we now have narrowed the scope of those number ranges. So from 40 to 200 to 140 to 200 and 100 to 200. Now if I click play and then we refresh and preview our cropped image, we see an even tighter crop there. So we're just zooming in now, just selecting and cropping on that one portion. We could change this range to anything within the shape values that we're giving here. So we know that it's width by height. That's the dimension of our new image as we've created here. So we could even use those values and say width divided by height and use those values to perform that crop function as well. Next, we have a bit of a more complex action, which is the function called Canny edge detection. So it's just going to be referred to as cv.canny, takes in an input image, and then essentially a kind of min and max thresholding values is maybe how you can think of them, but a min and max value, and then a kernel input. You could think of this like the kind of sampling size. So I would think of this as a min value as in color brightness minimum, color brightness maximum, and then you can think of this as a kind of sampling kernel size. So how big of if this was like a rendering, how big of a bucket would you be rendering this image with? That's how I like to think of it. It's maybe not exactly right. Again, check out the documentation if you want to learn more about this function. What is it going to do? It's going to create kind of cartoon-like line work representations. Now, important, not vector lines. It's not actually creating vectors. It's still pixel information, but it's representing it as line-like pixels that extract the edges of an image. So it basically takes the contrasting values of particular local areas, and then it draws those edges. This is really, really fantastic for machine learning. Why? This is trained many sketch to image or image to sketch, different types of machine learning models. So a lot of the generative AI models that have this type of feature are based on this algorithm. So it's been critical in a lot of the really amazing developments in machine learning over the last few years. So we're going to be able to actually perform this ourselves. How do we perform this ourselves? Well, we just need to input or adjust those values, input our image. We're feeding in our threshold value. If we click play, it's going to save out Canny Simple. Why is it called simple? We'll get to that in a moment. And this outputs our Canny image. So we output our image here. We see two things. We see that we have a particular output. We don't really know if it's good or bad because we have really no means to evaluate what a Canny edge detection is supposed to look like. However, we do know the edges of the image we fed in and what our eyes perceive. So this might look too noisy to us. We might try and get a cleaner output. We might try and get fewer lines picked up in the Canny edge or more lines picked up, higher resolution. These are the types of things that we'll use to evaluate the success of this particular function. What else? They're white lines on a black background. This is the default. if we wanted to switch this, we would have to invert this image. Now let's take a look at adjusting these input parameters. So what if I lower this value here? So it's now 50 to 150. Click play, refresh. Let's take a look at that output image. It looks like the density is actually increased slightly. It may be fairly close to what we had before, but it does look like we've maybe increased that density. So you might see more difference with other images. So go ahead and test other ones and see if you can make it clear how those parameters are changing the output value. So now, since those parameters don't change much in that particular example, this might not matter so much, but if we wanted to auto-tune those input parameters, we have a method to do this. Now, since this is not a comprehensive introduction to OpenCV, instead it's just a basic introduction to OpenCV and using some of those functions inside of Google Colab's Jupyter notebooks, I'm not going to get into this too much, but what this is doing is essentially reading certain properties from the image, adjusting certain values to give us the optimized input parameters for that Canny edge detection. So if we run this, it then gives us the kind of cleaned up best version and will output to our files as Canny advanced image. And we have a slightly less noisy, although still pretty similar, but slightly less noisy version of the Canny edge detection. What's one more thing that we can do? We might want black line work on a white background. This might be for a number of reasons. If we want that, what do we need to do to the image? We need to invert it. Well, it's already a grayscale image, which we know is ranging from 0 to 255 in each pixel value. So what do we want to do with that information? Well, if we wanted all of the 0 values to be 255 and all the 255 values to be 0, how could we get this? We could subtract 255 and then subtract from 255 our image pixel values. That gives us the inversion. So 255 minus the image gives us the inversion. We can actually just directly perform that math instead of looping through every pixel, because Python actually is aware of what that data structure of an image is. So we can just say 255 minus that, and it applies it to every single pixel in the image, which is pretty amazing. Otherwise, we can use a built-in function inside of OpenCV called bitwise not. What does this mean? It means basically for all the bits, all of the parts of the image, flip it, invert it, make it not. If it's true, make it false. If it's black, make it white, right? So totally invert it. If we add that here, run this, and then refresh our file, we can see that inverted image with our black line work on a white background. What's next? Well, what if we wanted to extract a silhouette or an outline around a particular object in an image? This is going to be called contouring. Now, the default contouring methods draws contours all over the image, but what we're going to look at is just extracting the biggest one. Now, what do we do for this particular method? We're going to use a threshold, but this time the basic threshold. Why do we use the basic threshold? Because this threshold actually gives us the threshold outline around all of our mathematical surface, which is slightly darker than our white background. How are we getting that extracted? Because we have such a tight clamped value from 250 to 255 that it's thresholding all but that object, meaning it's giving a kind of binary between the object and the background, which is entirely white. We're also using threshold binary inversion to flip which is considered black and which is considered white. So we're actually making a white object in the middle. So we're creating a mask around our object, which is now represented by this contour. How do we get those contours? With just a few functions here. We're importing a different library called imutils. Imutils allows us to grab the contours. We can then sort them by max area, max contour area here. So we're sorting that list. We can then just extract just one value. So we'll just extract the biggest one. We're then drawing those contours on our original image, which is represented here, but we can also click play to run it, hit refresh, and we can take a look at that contoured image. So we get a green contour drawn around our image. What if we change this threshold value? I'm going to change it to 140. So the min value of 140. We now have a looser clamping. What's this going to do? It creates a threshold that doesn't consider the entire object as one object. Why is this? Because it's basically taking the range 140 to 255 and considering all of that within a particular range for a threshold. So it's everything but that particular sliver. So we want this, for this image, we want this clamped pretty tightly. We can say 240, play, refresh, and check that image output, which gives us almost the entire contour. If we move this all the way up back to 250, hit play, and then refresh and check that, we now get that entire contour drawn around our object. So if we're getting it too big for our object, lower that minimum value, or adjust this kind of range between the min and max for this threshold input, and test it until it's working. So adjust those two parameters until it's doing what you expect, which is drawing the contour around the one particular largest object in your image. Now, what else can we do here? We could also change the color. So right now we have 0, 255, 0. What if we say 255, 0, 0? Hit play. What does this give us? It gives us a blue outline. What if we want a red outline? Change this to 0, 0, 255. And now preview that and we get a red outline. What about yellow? The yellow outline is both red and green, so 255 for both of those gives us a yellow outline. What if we want to change the thickness? We can do that because right now our thickness is 1. We can change to 2. Hit play, double click to preview our image, and we get a thicker outline, so a thicker silhouette there. So we can actually use this for representations to draw silhouettes. Let's say we can't do that for whatever reason from Rhino and we want to draw it very quickly. We could just use this function and draw it in a second. We could also use some other program like Illustrator or Photoshop, but we now can do it with our own Python script that we've created using OpenCV's method. What if we didn't want the exact contour of the object, but we just wanted a bounding box like in object detection using an AI object recognition algorithm? What if we just wanted the bounding box where that object is? Well, in this next script, we actually take the output of our contours and we read it in and make a bounding rectangle using OpenCV's bounding rect function. And using that method, we create the bounding rect with a given starting x, starting y, and a width and a height for that rectangle. How do we then draw a rectangle? We use the rectangle function in OpenCV to draw that rectangle onto a base image. We feed in our image. We're giving a starting point, and then it needs a second point, a second corner point, because we're drawing out that rectangle from 2 points. Well, what is that second point? X plus W and Y plus H. So it gives us the starting point and the bottom point, or bottom corner point, catty corner to that starting one. And then again, we can change the color or change the line thickness, and then we can output that image. Click play, refresh, and we now get bounding rect image, which draws that rectangle around our image. Lastly, what if we want to segment an image into particular patches? We can do this using clustering algorithms. What clustering algorithm? The watershed segmentation algorithm. If we scroll down, this is a much more complicated algorithm, so I'm not going to get into it in this video, but it basically just stacks several functions useful to us with from a couple of libraries, including the random library, NumPy, which is for arrays and array operations, imutils, and then CV2, which is OpenCV. Some of this initial stuff is actually somewhat similar to what we had before, but the new code starts here, and you can see that it gets quite intense. Again, if you're interested, check out the documentation. It's really helpful in learning some of these things. I may also post later on a more in-depth video describing some of the functions and properties inside of OpenCV, how to work with them, how to conceptualize them, etc. So what are the primary parameters we can interface with here? Well, I have left a few comments in this notebook. where I've said update the threshold minimum value below. So we have a threshold, and that's going to be one of the ways that we can actually change our outputs. Let's go ahead and take a look at adjusting these parameters. So let's just start with this one first. I'm going to click play so that we can see our output image, refresh our folder on the left. Once this finishes, so it finished, I can refresh. Where's our image? Segmented image right here. If we double click, we can see the output image. So this is basically segmenting patches that are kind of most similar across our object. First, it's taking a threshold, and then it's basically it's adding kind of markers based on certain areas of the image based on that threshold. So kind of patches of our image. So it's a way to segment different patches or groups or clusters of our image based on similarity. What if we adjust this threshold value? Well, if we clamp this up, so not 240, but we make it 250, we should see fewer patches show up. So if I click play, wait for it to finish, and then refresh and click our segmented image, we now see fewer patches. Why do we see fewer patches? Well, just like our threshold example before in our contours, when we decrease that range between the min and max for our threshold input parameters, we actually get more of the entire thing being considered one mask. So we're masking the whole object, giving just one cluster. As we get closer, so if I say 252 to 255, we should get even closer to just one entire mask around this object. Now we get one mask. What if we want more patches? Well, drop that value, refresh. Now we have a wider spread between the min and max value, and we should see more patches occurring. And we could continue to adjust that with the general principles of the spread as well as the pixel values, meaning 255 is a white pixel value and 0 is a black pixel value. So we're taking our input image, making a threshold based on the range that we're declaring here. And then we're taking that in, developing markers, which is the seeds for our cluster patches. So the more patches we have in our threshold, the more patches we end with in our clustering algorithm or our segmentation. If we wanted to save this image, we could right click, select save image, and we could save it directly from here. Or any of these images on the left as outputs, we can just click on the dots and select download, and it would download to our local folders or local hard drive so that it doesn't get deleted when we disconnect our runtime. What's another parameter that allows us to edit outputs of this segmentation algorithm? This float value of our second threshold, so this is after we've actually applied a distance transform and normalized our data, we have another value which is the float, but this does something very, very, very similar to this other one. So it's actually the same function, threshold value, and it's still about the kind of spread between that float 0.3 value and 1.0. So inside of this float, if we say 0.8 and hit play, refreshing that image and then previewing the updated version, we've masked it all out again. Why have we masked it out? Because we decreased that spread again. We've decreased the min and max spread. So if I lower that down to 3, hit play, and then we update that image and preview it again, now we see more clusters. Now if we lower this again, we should see more clusters, but past a certain point, we'll actually start over expanding the threshold, which it does an interesting thing. It actually creates larger clusters again. So it's all about a kind of sweet spot middle range for both of these threshold input values. So we can go ahead and test 0.1 to 1.0, which is almost the entire spectrum of that threshold. So let's see if it doesn't go back to one entire cluster. So it hasn't yet. So now we're seeing even smaller patches, more segmentation, more clusters. And these are running based on specific features, specific edges present in the image itself. So it's a really great way to mask a particular region. What if you're using a generative AI model and you wanted to use this to first filter an image and then only perform a generative AI operation on just one patch? you can do it. You can just select this lavender color, and using given kind of AI workflows, you would be able to just perform on that patch. Or alternatively, you could just use this inside of Photoshop and collage based on these clusters. It's almost like a render ID inside of many rendering programs. It allows you to better post-process your images. So that's all for this introduction to the basic functions of OpenCV. One more time, just to reiterate, if you want to save any of this, just click on the 3 dots and select download, or double click to preview them, right click and select save image. That's going to allow you to save that image to your local desktop so it won't be deleted after you've run through these. If you want to save the notebook with any changes that you've made, just go to File and go to Save, or Save Copy in Drive, or if you have a GitHub account, just go ahead and save that copy in GitHub. Lastly, when we're done with this, so after we've saved, File, Save, we want to go ahead and disconnect and delete our runtime. How do we do that? Click the down arrow, disconnect and delete runtime. That's going to wipe out all of the images that we have to the left, so keep that in mind. Disconnect and delete. And now we're ready to move into our third notebook.